I want to talk to you about one of my favorite examples, which is the differential equation dy dx is equal to y. You just solved this differential equation using separation of variables. Remember that to apply separation of variables, we need a differential equation of the form dy dx is equal to f of x times g of y. Here, f of x is equal to 1 and g of y is equal to y. And you found the solution to be the family of functions y is equal to c times e to the x. Note that the parameter becomes multiplicative when we solve for y. And recall that the variable x is unitless, so the units of this parameter c must be the same as the units of the variable y. We have to be careful to see what values the parameter c can take. You might think that c must be greater than 0, but we can test this and see that if y is equal to negative c times e to the x, then dy dx is equal to negative c times e to the x, which is equal to y. So the differential equation holds for c positive and c negative. We must test the case c equals 0 separately. In this case, y is equal to 0, and dy dx is equal to 0, which of course is equal to y. So the differential equation holds for c equals 0 as well. So the general solution is the family of functions y is equal to c times e to the x for c any real number. That is, the solution is the collection of curves for c positive, c negative, and c equal to 0. Note that I've drawn just a few of these solution functions. This is the solution for c equals 1, which is y is equal to e to the x. This is the solution where c is equal to 3, which is y is equal to 3 times e to the x. Here's the solution when c is equal to 0, which is y is equal to 0. And here's the solution when c is equal to negative 1, which is the function y is equal to negative e to the x. But really, there are infinitely many solution curves, but I can't draw them here because that would make this video way too long. Now we've met all the members of the family of functions, even the negative ones. So how do we pick out individual members of the family? The answer is that we use an initial condition. Let's look at an example. Consider our differential equation dy dx is equal to y plus an initial condition, which is the value of the function at one point. Let's say y of 0 is equal to negative 2. Then we know the solution is the curves y is equal to c times e to the x, and the initial condition tells us that y of 0, which is c times e to the 0, giving us c, must be equal to negative 2. So c is equal to negative 2, which tells us that our function is y is equal to negative 2 e to the x. And this is the unique solution curve in our infinite family that satisfies both the differential equation and this initial condition. There's actually a theorem that tells us when we can guarantee that we can find a unique solution function given an initial condition. We're not going to prove it, so I'm just going to state it here in the case of separable differential equations, which are the only differential equations that you are going to be asked to solve using formulas. So given a differential equation dy dx is equal to f of x times g of y, and an initial condition, y of a is equal to b, if f is continuous, g is continuous, and g prime is continuous, then there is a unique solution curve that satisfies the differential equation and passes through the value determined by the initial condition. Now it's your turn. You're going to solve some differential equations with initial conditions to find unique solutions. You'll see an example where the hypotheses of this theorem are not met, and an initial condition can fail to give a unique solution function in the next example video. Good luck!